Okay. I'm going to introduce our next speaker is Arthur Benjamin, and is talking on counting on the Hosoya's triangle.
Thank you, Ava. Thank you, and thank you to the organizers for running this magnificent conference. Thanks for having me here. I want to thank Rigo Flores, who is, I hope, watching it on Zoom, but is not able to be here this morning. But because it was a talk that one of his students gave 4 years ago, Matthew Blair, in Halifax, that prompted this problem. He was talking about a generalization or an extension of the Hosoya triangle, the determinant Hosoya triangle, which I'll talk about later. So, but anyway, I want to spend most of this time just having fun with the Hosoya triangle. You've seen a little bit of it at this conference, but let's really play with it this morning, right? It is if Pascal's triangle had a child with Fibonacci, you might have created the Hosoya triangle. And here's how it goes. You have on your triangle, you have Fibonacci numbers on the boundary, right? And inside the triangle, you have products. So if you look at this 3 and this 5, their product is this number 15. Okay, so you get that nice little parallelogram. Hosoya called this the 7-4 entry because this is row 7, entry 0, 1, 2, 3, 4, right? And it's equal to F3 times F4. I'll use the notation little h to say the third diagonal times the fourth diagonal, H34 as F3, F4. Okay, I won't use too much notation, right? So if you think of that parallelogram, we have the property that the 1 times the 15 is equal to 3 times 5, right? That's how the numbers were defined. But this parallelogram property extends to all parallelograms inside this triangle, right? And here you have 5 times 16 is 8 times 10, right? 2 times 6 is 4 times 3. So all the parallelograms have this property. You can see this one. I mean, the proof of this you can see. If this is FIFJ and this is FKFL, then their product is the product of those 4 numbers, and this is FKFJ and FIFL. So it's the same 4 Fibonacci numbers being multiplied. So that's why that parallel property works. It has a nice recursive property that if you take any number, and unlike the triangle that Earth mentioned to us earlier, instead of the Pascal would be adding these 2 numbers, right? But in the Hosoya triangle, we're adding the 2 numbers diagonally to the left, right? So this 6 is equal to 4 plus 2. But surprisingly, it's also equal to the sum of the numbers on the right. So if you've got 2 numbers in both directions, then that number will be both the left sum and the right sum. So that's kind of cool, right? 15 is both 10 plus 5 and it's 9 plus 6, right? And the only initial conditions you need to give are these 4 ones up here on the top. Right, and everything else has 2 numbers either to the left or to the right or both, and the proof just comes from taking your f sub m and expanding it, or your f sub n and expanding it, and you get the recurrence that way. Okay, I think Hosoya defined the recurrence first, which didn't quite seem well defined to say it's the sum and that sum. And then said, lo and behold, it's the product of Fibonacci's. I'm saying, no, we'll define them as the product of Fibonacci's and show that the recurrence works. There's some diamond properties of this triangle. For example, if you take the 4 ones at the very top and you add those numbers up, then you get this number 4 right below it. This is called downward generation. And it works, for any group of 4, 3, 3, 5, 5, they add up to 16, right? Let's go up. The upward generation is if we take in our diamond, if we add the numbers vertically, adding red will generally be adding because it's hot. right? And we subtract the numbers horizontally. Blue will be cold, it will be negative, right? So 9 plus 25 minus 15 and 15 gives us 4. So that generates the numbers that are going up. You gotta love this triangle, right? I mean, this is, I mean, playing with this triangle, I got to re-experience some of the same initial fascination that I had for Pascal's triangle and Fibonacci numbers. Like, wow, look at all these patterns, right? Here's rightward generation. If you take in your diamond 3 numbers and add the 3 numbers and subtract the rightmost number, you know, you get the number on the right, right? 10, 15, and 24 minus 16 is 13. If you add the 3 numbers here and subtract the number on the left, you get the leftmost number, right? I mean, it's just filled with patterns. Maybe one of my favorite properties that Hosoya calls the crawling crab properties, all kinds of very colorful names for these identities. The crawling crab property says, all right, if you take 3 numbers, let's think of a little triangle, arrow pointing down. 8 plus 8 plus 5 is 21, the Fibonacci number 21. 5 plus 10 plus 6 is 21. 6 plus 9 plus 6 is 21. Imagine doing sort of a crab walk along these 2 rows, and no matter what you get, you're adding up to the Fibonacci number 21 in this case. If we took a different row, like say 13, 13, 8, that adds up to 34, as does 8, 16, 10, 10, 15, 9. That's the crawling crab property. All right. The inverted crab property, if instead is kind of crawling forward, now you have an upward arrow pointing. And now if you take 13 plus 8 minus 8, you get 13, which is a Fibonacci number, right? 8 plus 10 minus 5 is 13. 10 plus 9 minus 6 is 13. You gotta love this triangle, right? Here's a very simple property that I call it the vertical neighbors property, right? Just take 2 vertical neighbors, 5 plus 8, 3 plus 10, 4 plus 9. You always get a Fibonacci number. You get 13, right? In Pascal's triangle, there's a nice identity called the hockey stick identity. When you add along a column, you get another binomial. Adding these binomial coefficients, you get another binomial coefficient. The same thing happens in the Hosoya triangle. You add 1 plus 1 plus 4 plus 9, we get 15, right? Doesn't matter whether I move the hockey stick to the right or to the left, I'm going to get 15. Right? If I do an off-center hockey stick, let's see here. So like 3 plus 5 plus 16. Do I bend to the right or do I bend to the left? Well, if you have an odd number of terms that you're adding, you bend towards the center of the triangle. So 3 plus 5 plus 16 is 24. 3 plus 5 plus 16 is 24. You bend towards the center. Whereas if you have an even number, and here's another one, 2 plus 3 plus 10 is 15. Whereas if you have an even number, like 1 plus 2 plus 6 plus 15, that's 24, you bend away from the center. All right, so that's the hockey stick property of Hosoya's triangle. There are some identities that are not quite so visible from the triangle, but just like with binomial coefficients and Fibonacci numbers, they are there nonetheless. For instance, here's a trickier one that uses the Lucan numbers. We all know and love the Lucan numbers 2, 1, 3, 4, 7, 11, and so on. If you take, starting with the simpler one, if we go down the center of the triangle, if you take 5 times a center number, like 4, then you get a Lucan number plus or minus 2. Right, so 5 times 4 is 20, which is 18 plus 2. 5 times 9 is 45, which is 47 minus 2. 5 times 25 is 125, which is 123 plus 2. Right, that's the central property. More generally, if you sum down any of the of these we have, oh, not summing, if we just take, like what happens if I take 5 times this number, I get 10, you get, it's a Lucas number plus or minus L sub m minus n, all right? So 5 times 2 is 10, which is 11 minus 1. 5 times 6 is 30, which is 29 plus 1. 5 times 15 is 75, which is 76 minus 1. Why am I always adding and subtracting ones? Because even though my parallelogram keeps going out, the difference between the left diagonal and the right diagonal is staying constant at 1. So anyway, so lots of identities. So of course you should ask, and if you don't, I will, what are these numbers counting, right? I mean, anything that has all kinds of beautiful identities has to be some kind of counting problem in disguise, right? Well, okay, so let's review what do Fibonacci numbers count, right? They count tilings using squares and dominoes. So how many ways can you tile a 1 by n board with squares and dominoes? There's one way to tile a board or a strip of length 1, 2 ways to do length 2, 3 ways, 5 ways, 8 ways to do a board of length 5. Why are there 8 ways? Because your strip is either going to be a strip of length 4 followed by a square, that's these 5 tilings, or it's going to be a strip of length 3 followed by a domino, that gives you those 3 tilings. Right? So these numbers begin like Fibonacci numbers. They will continue to grow like the Fibonacci numbers. Therefore, they are the Fibonacci numbers. So for at least for me, whenever I think of Fibonacci numbers, I'm thinking about tilings. What's the tiling interpretation of what's going on? So what do the Hosoya numbers count? Well, if HMN is FM times FN, then that's counting pairs of tilings, right? Either, so this number 15 counts the number of ways I can create a 2 tilings, A and B, where A has length 4 and B has length 3, because there are 5 ways to create A and 3 ways to create B. H32 is 6, because it counts tilings of length 3 times tilings of length 2. There's another way to think of these that's also convenient. So again, you can think of it as choosing one from, I was going to say column A and one from column B, but I guess they're row A. So choose something from row A, choose something from row B, or if you put those things together, what you create is a tiling of length 5, right? 3 plus 2 is 5. But if I do my A tiling followed by my B tiling, these are going to be tilings that are breakable at length at the 3rd cell. Or the way I wrote it here, if I put my B tiling before I put my A tiling, I'm going to create a tiling of length 5 that's breakable after cell 2, right at cell 2. Okay, so these are breakable tilings. Is another way to think of these Hosoya numbers. Right? So here, these are the how many tilings of length 5 are breakable at cell 2. There are 6 such tilings, and here they are. Okay. Any questions on that? And so that's the way to visualize the Hosoya numbers. Obviously, by the symmetry of the triangle and by the symmetry of these tilings, there are just as many tilings that are breakable at cell 2 as there are tilings that are breakable at cell 3. Just flip these around 180 and you get that. These interpretations allow us to create combinatorial proofs for all the identities you've seen and more, right? So let me just do a handful of them just to give you a taste. And then at the end, I'll show you what those determinant Hosoya triangle identities are, numbers are counting as well. All right, so let's start with maybe the easiest one, the vertical neighbors property, right? 5 plus 8 is 13, 3 plus 10 is 13, 4 plus 9 is 13. In Fibonacci language, this is saying F3 squared plus F2 squared is F6. Right, now, these all have been done in the past combinatorially, but let's just see what they're saying here. How many tilings? So if I look at this identity, how many tilings are there of length 6? By definition, F6. How many of them are breakable at cell 3? Well, I have three ways, F3 ways to tile the left side, F3 ways to tile the right side. So there's F3 squared such tilings. How many are not breakable at cell 3? Well, to be not breakable, that means you've got a big fat domino covering the break. And now you have F2 ways to tile the left, F2 ways to tile the right. That's F2 squared. So every tiling is either breakable, or every tiling of length 6 is either breakable at 3 or not breakable at 3. So F6 is F3 squared plus F2 squared. How about minutes? Oh, 5 minutes? Whoa. All right. Let's do, does that mean I'm at the 20 mark or the 25 mark?
Up to the 20 mark.
Okay, good. All right. In general, I mean, one of the advantages of doing combinatorial proofs is allows you to see patterns that you might not have seen otherwise. Like F sub n, if you break it at cell k, this is still the vertical neighbors property, is fk, fn minus k, or if you have a domino, fk minus 1, fn minus k minus 1. The crawling crab identity, that might be my favorite of the bunch, right? That says these numbers add up to Fibonacci numbers. How many tilings of length 7 are there? So how would I explain this identity? Well, there are F7 tilings of length 7. How many where that is the third cell is either covered by a square, the beginning of a domino, or the end of a domino, and that's what gives you those 3 terms. The inverted crab property. Now I can say we could do the inverted crab property just by quick algebraic manipulation and turning it into the vertical neighbor identity. Let's see if we can sort of purely do it combinatorially. Because you have to be breakable 2 consecutive breaks, cells, one of them has to be breakable because your dominoes are only so long. So a tiling of length 7 is either breakable at 2 or breakable at 3, but we've overcounted because it might have been breakable at both if we had a square there. And that's what gives us that identity, right? The hockey stick identities, given my timing, I'll just flick through these, right? But the central hockey stick identity says the sum of the squares is Fn times Fn plus 1. Here's a tiling of length n, here's a tiling of length n plus 1. That's annoying. Well, you have lousy timing, thank you. And look at the last fault line, right? Where is the last fault line? And that will give you, after the last fault line, there's only one way to tile. You have to have a domino here, a domino here, a domino here, a square there. But you have complete freedom on how to tile the 4 cells before and the 4 cells before. So that's what's going on there. I'll skip the more general hockey stick identities. You just draw a slightly different picture and you can get that as well. The trickiest identity, I don't think I'm going to have time for, but I'll just give you a whiff of what that's about. How would you prove that 5 times this product is a Luca number plus or minus a Luca number? Essentially, we're trying to show that now the Luca numbers count bracelets. That's tilings where you have where you're allowed to cover the clasp, where you're allowed to go from cell n to cell 1 with a domino. The basic idea is for every tiling pair, we're going to create 5 bracelets, right? Every tiling pair of length m and n, we're going to create 5 bracelets where those bracelets have length m plus n plus 2. And 3 of those bracelets are trivial to create. You just, append y to x, and now then attach 2 squares, or attach a domino, that covers the clasp. So those are the 3 trivial bracelets. And then bracelet 4 will depend on how x and y end. It involves 3 cases. Bracelet 5 involves 6 cases. And I certainly don't have time for that. So the last thing I want to mention is the determinant Hosoya triangle, which is what started this all. investigation for me. And it's the same kind of triangle. It has the same recurrence. 9 is 5 plus 4, 9 is 7 plus 2, but it has one little change to the initial condition. That 0 used to be a 1. That's a 0. That's the only change other than the recurrence, right? And the question is, and the question I asked of the student 4 years ago is, hey, he showed it had all kinds of beautiful properties. I said, what is it counting? And he didn't have an answer then. Since then, he and Professor Flores did create some interpretations, but I think what I have here is a little bit cleaner. I was talking with Roberto this week. In fact, his initial conditions were these 4 numbers. I said, no, you want to make them these 4 because then this one directly compares to the other one. And he agrees. And what these numbers are counting, the numbers inside the triangle, give me a Fibonacci numbers on the border, but what you have is a product of Fibonacci's minus another product of Fibonacci's, okay? They call it the determinant Hosoya triangle because if you put your Fibonacci numbers in a little matrix, it's the determinant of that 2x2 matrix. This triangle has many of the same properties as the original Hosoya triangle. You can check for yourselves. I knew I'd be close to the end of my time. You can check for yourselves that it satisfies things like the vertical pairs identity, right? That they add up to Fibonacci numbers. The downward generation still works. The crawling crab property still works. The inverted crab property still works. And and I should have said at the very beginning, this is work that was done with my senior thesis student, Daniela Elizondo. So after hearing the talk 4 years ago, I said, Daniela, I've got a good senior thesis project for you. Find out what these things are counting and come up with combinatorial proofs on Hosoya's triangle and the determinant Hosoya triangle. And that's what she did. Daniela is now a first-year PhD student, just finished her first year in math at Rutgers University. And and finally, what are these things counting? They're counting tilings of length m plus n that are breakable at m, but do not have 2 squares surrounding the break. And with that interpretation, we can find combinatorial proofs for many of the determinant Hosoya identities that we've seen before. And I'm at slide 89, so I'll stop here. Thank you very much.
Are there any questions for us?
Sure. Okay, so maybe another question. So what happens if you take a non-Fibonacci at the border by like Fibonacci?
Indeed, what happens? I haven't swum in the Fibonacci seas like Rigo Flores has, and he might know the answer to that question. I was just starting with, okay, what does the Hosoya or this determinant Hosoya, what are they counting, and what proofs identities can we do through combinatorics? But that's a fair question. Because this triangle has been around for so long, it may well be answered, but I'm not an expert on that, so I don't know. Other questions? Okay.
I was just thinking of the tiling interpretation. That should be pretty simple.
There probably is. There's probably a. You know, I'm wondering is if you did the Fibonacci, if you put Fibonacci's on the border, I would imagine you would want to sum the previous 3 instead of the previous 2. So if you mix and match, maybe you get something uninteresting. But you know, my guess is instinctively is I want to add the previous 3 instead of the previous 2. Other questions?
So, I love the rectangle or the parallelogram area. Could you generalize this to a tetrahedron? And try to make this 3-dimensional. You either have tetrahedrons inside the tetrahedron or boxes inside a tetrahedron.
You know, I mean, I think two things that come to my mind when I'm thinking about adding dimension to these numbers are, you want to add dimension to the Pascal triangle, no problem. Instead of binomial coefficients, you have multinomial coefficients. You want to add dimension to the Fibonacci numbers, that does become a problem. That is, if, for example, tiling with squares and dominoes is equivalent to tiling a 2 by n board with just dominoes, right? Because dominoes can either go horizontally or they can go vertically, but that's like a pair of squares. So if you tile everything with dominoes and then split it in half along the middle, you get a normal square domino tiling. But as you know, once we get beyond 2 by n, we're looking at m by n tiling with dominoes, though the answer is known, and it's a beautiful answer involving a product of cosine squared this plus cosine squared that, Castellan's formula, it's not easy. So I think that because of the Fibonacci nature of this, when we add a dimension to that, I think it'll get hard. Again, I'm no expert in Hosoya triangles.
Right, just throwing this out there.
Yeah, no, it's a wonderful question. My instinct says it'll be a hard question,
Right.
knowing how hard even the question of tiling an m by n rectangle with dominoes is.
But hopefully brute force would give you the image, which you could then start investigating problems.
Sounds like a great question. I agree. Other questions?
Yeah, you showed that inside the triangle there's, for example, that number. Do you think that there may be also various other numbers, just tiny numbers?
Very possibly. I was asking Rigo Flores this week. I said, basically, Daniela took all the identities she could find from Hosoya's original paper and some of the papers that Flores and his collaborators have put out. Since then, he's put out even more. And so like I was asking him, I said, for instance, I said, gee, I don't even see what happens when you sum the rows of the normal Hosoya triangle, right? You could start on 1, 2, 5, 10, 20. It starts looking promising. Maybe these are Catalan numbers or something times 5. And then, but then the next number is 38, and the next number is something else, and go, is there anything that's going on there, or is this just one of those hard things to do? He showed me a paper. He said, oh yes, it's this is like this row adds to the Lucan number that's 2 beyond it times m plus 1 divided by 5, and minus 2 times the Fibonacci number. It was a pretty simple expression. It was like m plus 1 times L n plus 2 minus 2fm over 5. It was reasonable. Oh, okay. There's a lot of interesting things going on here, a lot of patterns that don't meet the eye. And be wonderful to find combinatorial proofs of these. So if you go to rigoflores.com, you can see his papers that have a whole bunch of more of these identities that are just waiting to be explored combinatorially. And I encourage you all to find these. So I think, yeah.
Have you tried to use any symbolic software to get identities? Because you have a lot of identities by using several groups to sum, but maybe most of the sequences are recursive sequences. Maybe
Sure.
you use symbolic computation.
I have not gone the symbolic computation route, but sure, that's an option. Doing the generating function route is surely a nice option for discovering and understanding these. I kind of went with my hammer, which is the tiling route, and just to see as a challenge what could be done.
It's almost like the diamond at the top is the stem cell niche for the triangle. So if you change the 1 to a 0, you've got your rules and it changes the organization of within the triangle.
I do believe that's right. I think if you change these numbers here, it, you know, just like when you change the initial conditions of the Fibonacci sequence, you still get tilings with squares and dominoes. You just have to give a certain extra weight to the first square, to the first tile, whether it be a square or a domino. And I imagine that you change these and it just creates some kind of weight or restriction on the tiling pairs from there. I'm that much I can feel pretty confident about. But yeah, that diamond is your initial conditions, and everything else is sort of governed by the reference. Thank you very much.
Okay, thank you.